Hello everyone, my name is Viraj and today we'll be looking at the 17th problem from the CP31 sheet by TLE eliminators under the 900 rated questions. Let's go. So moved on to my sheet, ticked off 900 and let's go to the 17th problem, array cloning technique. Okay, let's read this. You are given an array A of n integers. Initially there is only one copy of the given array. You can do the operations of two types. You choose any array and you clone it. After that, there is one more copy of the chosen array, or you swap two elements from any two copies. Maybe that can be the same copy on any positions. You need to find the minimal number of operations needed to obtain any or a copy where all elements are equal. Alright, great. So let us generalize this problem quickly and see what are they asking over here. Very simple stuff, alright, fun to imagine. We have an array A, alright, of n size. So I'll say I have this n variable and this array A. Let's say I have some numbers over here, some random numbers. Let's say A1, A2, A3, so on till an. Now what is my target? I am trying to basically get some array which has all elements equal. To fulfill this target, I have been given two types of operations. Okay, what are the two types? One type says that we can actually pick up any array, or to be specific, in the start we have only one array. We pick up an array and we clone it completely. So now that we have two copies of that same array. So let's just say that this is my array right now. Let's say A. So maybe I clone it and now I have a new array. Let's say I'll call that A dash, which is basically A only, right? I can say that A dash is basically A. So now I have two arrays. One is A, one is A dash, both are same. This is cloning process. So this is called clone. Or the other thing is you can pick up either the same array or two different arrays and you can make swaps. As in, let's say that this is, let's say the A dash array, it's the same, okay? So for example, let's say this is A1, this is A2, this is A, so on till AN. Now what I can do is, if I want to say I can make swaps, I can maybe say I would make swaps in two different arrays, or I can make swaps of elements in the same array also. So maybe I'll say, let me pick up this A3 and let me pick up this A2 and let's swap them. So now A3 comes over here, A2 goes over here. This is one swap. Or maybe I pick up A2 and A3 and I just swap it like this. All right, maybe something like that. That's also in the same array. That's fine also, right? So you have the ability to swap in one or two arrays. All right, why one? One means basically the same array. All right, this is like saying same array or two arrays. And this is available. You have swap two elements, to be specific. This operation is available. So either I clone an array or I swap two elements in one or the same as an or two arrays. This is what is given to me. I want to minimize this count of operations, how much I perform, to get, what's the target we discussed initially? To get some array which has all the elements same, as in A1 to whatever it has till the end of elements, everything is same. Alright, so we'll actually get a better idea when we look at the test case. Let's actually pick up some test case and see what is the idea over here. So let's say 0, 1, 3, 3, 7, 0. Okay, so 0, 1, 3, 3, 7 and 0. So I want that first I'll clone this array. So when I clone this, this becomes 0, 1, 3, 3, 7, 0. I have one more array that looks like this. All right. Now I don't need to name it, just follow with the whole process. Let's say this is one array, this is the other array. Now I can perform swaps. How many swaps do I would prefer to perform? I would prefer to perform exactly two swaps. What I can do is, just for ideation purpose, I can say that I'll pick up this 3 and let's say swap this 7 and pick up this 3 and swap this with this 0. So what my new two arrays look like, they haven't been modified. This looks like basically 3, 3 over here and that 7, 0 have come over here. Now remember the operations. How many operations have you done so far? You did one to clone the array and then you did two swaps. Okay, great. Now what I'll say is, I would want to now clone this array again. So if I clone this array again, this becomes 0, then this is 1, this is 3, 3, 3 and 3. Now I have three different arrays. Of course, I'm maybe assuming I'm maintaining or whatever you can assume. I have three different arrays now, and this is like array, this is array, so this is array 1, this is array 2, and this is the third array, which is basically the clone of the first array. To do this clone, I did one more operation, so I'll add it 1 plus 2 plus 1 again. This is the cloning part. Now, what I would do is maybe I pick up, let's say, this 3 and this 3 and swap them with this 0 and this 1. So basically 2 swaps again. If you do that, now you can imagine that this 3 have come over here, and you can say this 0 and 1 went over here. Now you did 2 more swaps and this is 2. Now don't you think that you have actually received what you wanted? Check the first array. It's all equal, all 3s. This is what we wanted, this was the target. And what is the pattern that we followed? We first cloned, then we did 2 swaps again. Then we again cloned and we did 2 swaps again. So we have totally executed 6 operations, 2 cloning process and 4 swaps roughly. And we have definitely achieved the target. So now I think the idea should be clear. Now we are arguing, of course, that this 6 is the lowest we can go. And that's why we are saying that you can say answer for this case is 6. Alright, now you can try to run a rough idea on the other cases also. Pause the video and maybe you will come up with some approach. Try this problem on your own and let's come back. Great. Okay, so now let us try to see that we have understood the sample case. We have understood the problem also clearly. Let's see what's the expected time complexity in this problem. Okay, so I know that 1 second basically allows me 10 raised to 8 elementary operations. Now it's given very clearly that time limit per test is 1 second, which means that if I talk about one test only, it's 10 raised to 8 operations. Now, when I go back and see the number of test cases inside a test, that's 10 power 4. But we can also see that for every test, you can say, all the test cases, the summation of n over all that does not exceed 10 power 5. So I don't need to figure out the number of operations on an average for the test case. Rather, for the whole test, that is 10 power 8, I can try to estimate with respect to n. Which means that now if I look at n being 10 raised to 5 order, or to be specific, this part is more important. That is, it does not exceed 10 raised to 5 order. I know that for one test, basically I'm comparing with n roughly as 10 power 5 limit. Now, if this is the comparison, what is the expected time complexity? I know that O of n solutions will work. A little higher than this, maybe O of n logs n solutions might also work. Not necessarily I might create that, but it's still going to work. But O of n square solutions are a problem. And n square roughly estimates that no brute solutions, by the way. So n square solutions are something I don't want, right? And of course, anything higher than that is not possible. But solutions in like n log n powers or roughly O of n or up till down to the limit, if you are able to create a constant solution, all of that is good to go. And this is my expected time complexity discussion. Now, this is very useful because what it is telling me is I don't want brute solutions, all right? And that should be a very important point. Why? Because in this problem, when we figure this whole implementation also, or we figured this whole idea of how did we clone and come up with 6 operations, just with the sample case, for example, you might start thinking that is it possible for me to actually simulate this whole process of maybe maintaining different arrays and swapping them? Actually, that's not possible because you don't have a very high limit that's allowed. You are looking for a solution that's like n log n or n, which means I would need something smarter than this. Maybe I simulate this for myself, but I cannot actually bring it down to code. I would need a better idea. All right, great. So this is the importance of expected time complexity. Now we have a rough idea. Let's start. So what's my first intuition in this problem? All right, I have an array right now. Okay, I'll take the same array. This is 0, 1, 3, 3 and 7 and 0. All right. Now it's very obvious that I want to minimize the operations to finally get some array which has all numbers to be same. The operations that are available to me are never going to change the initial elements in the array. That means, let's say in the array you have right now 0, 1, 3, 3 and 7. Overall, these are the numbers only where everything is going to happen. As in, they might swap places, they might go somewhere else in the arrays, but there is no other new number like 2, 5 or any other number that will come into picture. This is very simple. It's basically simple common sense. Why am I saying this is because this means that maybe we can already try to estimate or see which number is actually the ideal candidate to take up an array where all numbers are equal to that number. What's the idea over here is, if we look at, for example, 3. What is so special about 3? 3 has the highest frequency. Alright, I mean 0 also has that, 0 also has 2 frequency, but 3 to be specific, like I can just take my casing with 3. 3 has the highest frequency right now in the array. Now, don't you think if I say 3 is my candidate, as in I fixate that I would try to make an array which has all 3s, then I would greedily be in a better situation. Why would I be greedily in a better situation? Because greedily, since 3 already has the highest occupancy in the array, later on when I start the cloning and swapping process, I am much more closer to create all 3s, since initially only I have the highest number of 3s or the highest frequency of that number. So 3 is definitely or greedily a good candidate for me. If I focus that I would prefer to make the element that has the highest frequency to be the actual number that is present everywhere in the array, then I would greedily, of course, minimize my operations. Okay, I would definitely require lower number of operations to make 3 in this case my number which occupies the whole array. This should be clear. Now in this case it is 3. Basic idea is pick the number with the highest frequency. Greedily this should work. Great. So this is our observation, and now this observation is going to, or this initial intuition is going to help me fixate that let's try to see what happens when we clone and what happens when we actually swap. Okay, so I'll take this to a new page. You have 0, 1, 3, 3, 7, 0. Let's just track the number of 3s right now. Number of 3s right now is 2. Now, I right now have 4 places which do not have a 3. I of course want that. Now, if I want more 3s, I would first obviously require those 3s. And how can I do that? I would need to clone the array. So my next observation would be that it makes sense my operations should start by cloning the array right now. Because if I need more 3s, I of course want a clone. So let's just clone this array and say 0, 1, 3, 3, 7, 0 came over here. Now, because I was tracking the number of 3s, I can imagine that the number of 3s have now become 4. Yes, I can imagine that. I have, of course, 4 3s now. But they are not exactly in a same array. They are in 2 different arrays. So this means that right now I was trying to solve a simple problem that I need more 3s. Now that I have actually done the cloning and I have more 3s, I would now want that they come to a single array, right? That should make sense. So to do that, of course, it would make sense that all the new 3s that were created, I want those copies to be swapped back to, let's say, some same array. And to do that, the number of swaps is basically equal to whatever was the current number of copies. So I would have said, right now, or starting off, you had 2 copies. You copied or cloned the whole array and you got 2 more copies. I would swap these 2 copies and bring them in the same array. This is 3 and 3. Great. Now, imagine we are still focusing on the first array. It's much more closer to all 3s. We only have 2 places to fill in this array now. Great. So let us do something greedy. What would I want to do right now is I would say, okay, now since I want more 3s, that is basically in this case 2 3s, let's actually clone the array again because I need to generate more 3s. But the question would be which array to clone? Of course, I only have left over one array which I can clone. So I'll clone this array and I will say, okay, now this becomes 0, 1, 3, 3, 3, 3. And now I have 4 more 3s. So I can say my count of 3s has actually gone to 8. Is that right? And now I can say that right now I had 2 positions to fill. So let me just pick up these 2 3s and make them come over here. And this would basically mean that I have done 2 swaps, which is basically the leftover swaps, and this is 3 and 3. Okay. And now you can imagine that this actually would be 1 plus 2 plus 1 plus 2 only. That is basically 1 cloning, 2 swaps, 1 cloning again, and 2 swaps, which is 6 answer. But now this 6 should also greedily or intuitively make sense that yes, this is the lowest, because we have greedily structured our argument in such a way. We selected the element that has the highest frequency since it would minimize the operations, since it's much closer to creating an array that has all the numbers equal to that number. And also we understood the cloning and swapping back part. So cloning was important, and after that you did the swapping. To be specific, now you can, if you make more cases, generalize this and understand that I am greedily trying to do a clone, then a swap, alright, then a clone, then a swap, alright, not a swap, some amount of swaps, and then a clone again, and so forth. And how many times am I trying to do this, to be specific? Remember, I was tracking 3s over here. When did you actually stop? What do you think happened? The count of 3s became 8, alright? Or to be specific, you can now imagine that the number of 3s went above the required 3s. You had required 6 3s, and now you have 8 3s. So you want to stop. So you know that you can imagine that this is sort of now a very implementative and a simple greedy problem, right? I can try to run some sort of a logic where all I would want is to maintain the variables which contains the frequencies and track the number of operations which I'm doing. I can first say I would clone, then I know that the copies have doubled. I can use those extra copies to fill up whatever places I would want by swapping till I can. If I want more spaces to be filled, again do a clone. Let's make those copies into use. Again do a clone. Let's use those copies again, and stop when I feel that I have enough copies now and I have crossed the limit of total size of the array, that is n. Alright, so this is like a rough idea. This is what the problem dictates. And now this whole idea is going to work very cleverly, because what we would imagine is we are not exactly going to maintain these arrays. We're not going to say that we are actually swapping. We are identifying the places and making the swaps. No, neither we would say that if we clone the array, are you maintaining a new array structure in general? No, that's also not true. What we would only maintain are simple variables. Just maintain the frequency and double it, and then get the swaps. So it's all mathematics that is going to get involved. Hence this problem is going to get solved, because now the brute idea is something we are not implementing. We are implementing a definitely quicker idea where we are getting the operations very, very quickly. Alright, so I'll give you a pseudocode of what we are trying to imagine. We'll say that, let's say we have an operations variable, which is initially 0. And we have, let's say, a current highest frequency, some sort of a variable. We can say this, let's say, current frequency, okay? Now this current frequency is of course the highest frequency of the element or some element that was coming in the array. This is current frequency. Now we would want that, let's run some sort of a while loop which says, till I feel that current frequency is less than n, don't stop. This should make sense, because if current frequency, that is right now, the element that I wanted to fill the whole array has the number of frequencies less than n, I don't want to stop. I want it to be greater than or equal to n. Either it becomes n or goes above it. That's when I want to stop. So till it's lesser, keep working. What do you want to work on? You want to say, let's start with clone first. So I'll say, okay, to clone, I would imagine that my operations have incremented by 1, because this is cloning. I would say, yes, cloned the array, operations got incremented by 1. Now, since I have cloned the array, I have twice the number of copies, right? And can imagine that I have twice the number of copies. So I need to keep a check. These copies that have now come into picture, do I need to use all of them? As in, do I need to swap all the new copies back in the main array or the first array that I was targeting, where I was trying to fill up or accumulate all the numbers to be same? Or do I have lesser requirement? I need to check that. How do I do that? I can simply say that if I feel that the current frequency that I have of the track that I was keeping of the number, if doing it into 2 keeps me within the boundary of n, that means I know that I would want to utilize all the copies, right? Because if I swap all the copies back in the main array, I still am in the main array having a frequency that is lesser than equal to 2, because now that new frequency has become into 2. So if that into 2 frequency is also still less than equal to n, then I know I have still more to work with. And in this case, I would be utilizing all the copies to be swapped. So I will say number of operations get added with how many swaps? Of course, only current frequency. All right, whatever is the current frequency, that number of swaps. Why is that? You can imagine that, like, let's go first back to the example. Over here, you could have seen that when he did the initial cloning, then you had 2 more 3s, and then you utilize all those 2 3s back. So you can say that whatever is the current frequency, when you would have cloned it, the current frequency is the amount of swaps you would have utilized to bring it back to the main array. Right, I hope this visualization is clear. So operations increment by that much amount. And now that it has been done, I can increment my current frequency to go equal to 2, which means basically it is now twice of what it was before, which indirectly signifies that now in the main array which I was imagining, I have the track of the number I want to make my array fill up with has double the copies, and the new number is now again stored back in current frequency only. This is like writing into equal to, so you get that part. All right, so this is the if case. Else, now else means that current frequency into 2 is actually greater than n, which means now that you have cloned the array, but you are not trying to use all the copies, right? Places are less to fill, copies are more. We can see that by over here. When we did the last cloning, we saw that we had 4 3s. All right, remember you had 4 3s, but you did not utilize all the 3s, right? You only utilized 2 3s, and you brought basically this 0 1 should have come over here from this position back at this location. So we can imagine that we did not utilize all the 3s. We only wanted to use some number of 3s, since I knew that all the copies were not fruitful. So I could have said that in else case, I would have said now my operations would have just incremented by how much? N minus current frequency. N minus current frequency is simply going to tell me what is the leftover places that are there. All right, they are of course something less than what was required. So I'll just get that part, N minus current frequency. So this is like current underscore frequency, and operations is this much that is added. And now current frequency, I can brutally make it to be like equal to N. All right. And this is what is my overall pseudocode. So now doing this whole structure, once you actually make current frequency to be equal to N, or as soon as it like quickly goes greater than equal to N, whatever be the case, you would be exiting this while loop. And every time you have made sure that you are cloning. So this is the part of cloning. So first time you do a clone, and next time you take a choose decision, informed decision. Do you want to swap all copies? All right, this is like all copies. Or do you want only some copies? All right, this is like some copies. You make that decision and you increment your operations accordingly, and you increment or double your, or whatever you can say, change your current frequency accordingly. All right, so this is the main idea. I hope this is clear. I would highly suggest that you pause the video. All right, run this through your head, that how would you have implemented some piece of structure that helps you clone, then swaps, then clone, then swaps, this whole idea. Of course, maintaining that you need the number of swaps to be how much you want, and cloning has to be done every time, every alternate manner, and where do you want to stop. All this should come into your mind. You can pause the video, maybe figure out some implementation on your own. Should not necessarily be something like this, right? It can be something different. It's just an implementation difference. For me, I think this is the best way I can approach this problem. All right, so let's move on to the code part and just see this getting finally executed. Simple enough. I have bigger variables over here. I have T, that is start of the test cases. I have N, I have the array, I take the input. Simple enough. Now I have a map. What I would utilize in the map is to get the frequency. So this is basically going to be getting the frequency of every number. And why do I need that? Because I of course want the frequency that is the highest right now of any number. Number doesn't matter, but I need the highest frequency to start with. So current highest frequency is initially 0, and I can just go in the map, and then every time I can just compare my current frequency to max out with itself, and I dot second is basically the stored frequencies of every number in the map. So I dot second is that I get the max out of this. Now after I end this loop, of course, I know I have well secured the current high frequency in the array. Now I have this operations variable, which is basically my answer, starts with 0. Till current frequency that I am maintaining, current high frequency that I am maintaining is less than n, I would want to do this clone. So operations plus plus. Then if I have cloned, I have twice the copies. Let's see whether all are required. If all are required means is the double still less than equal to n? If it is, increment your operations by that amount and double it. Else, you know that not everything is required. How much is required? Only n minus current frequency, that difference is required. Let's increment your operations by that much amount and current frequency directly becomes n. And now, of course, this while loop ends as soon as you know current frequency has gone greater than equal to n and you print the operations outside. Alright, so this is the whole problem. Now what about the time complexity? We have an n order over here to take the input. We have the n order over here to take an again loop for 0 to n. But then since we are using a map over here, so map would have extra log n complexity for insertion. So we can say this is like n log n into log n for every time insertion is done or updation is done, whatever you can call that part, since this is a simple map. Then we have this while loop. Now estimating this while loop time complexity is simple enough. What you can imagine is assuming current frequency is very, very low right now and n is very, very large right now. You can understand that every time you are making current frequency to go its double amount. So basically you are starting off, let's say, a very small number, doubling it, so into 2, into 2, into 2, into 2, so forth and so on till you reach n. That whole idea is basically log base power, as in this loop will run in log base 2 of roughly n solution, right? Because you would be trying to capture current highest frequency to go into 2 every time again, and as soon as it goes above n you would stop. So that means log base 2 of n is the maximum number of iterations you would be running this while loop. Alright, so roughly this means that I have a time complexity, and since assuming this is of course pretty much constant, so I know that the time complexity is coming from this n over here, then n log n and this log n simply. So I can say that n log n is actually the better term to report because this is the largest term. So I can say n log base 2 of n, and now n being in 10 power 5 order, I can estimate that this is like 10 power 5. So this is like 10 power 5 into, this is writing log base 2 of 10 power 5 again, and this is going to be roughly like log base 2 of 10 power 5 is roughly like 17 to 18 operations. I can say upper max like 20 operations. So this is like O of 2 into 10 raised to 6. Alright, roughly something like that, because you would get 10 power 5 into 20, so that's 2 into 10 power 6. Now 2 into 10 power 6, or let's say 10 power 6 order, is definitely less than that 10 power 8 order, and this is like that n log n complexity which we initially also discussed, that is good to go. So yeah, this is great. This definitely solves the problem for me, and space is simply n, no need to bother with that part, which is only O of 2 into 10 raised to 5 order simply. Alright, this is the space complexity. This is of course coming from the size of the array. Okay, great. So this is all that is there in the problem. Alright, very greedy based, very implementive based. Alright, this piece of code that I've written over here can be mapped or can be written in any sort of other format you think is fine with you, as long as you get the idea of cloning and swapping and cloning and swapping in an alternate way. And the intuition should be clear. Where do we start off with? That's the highest frequency, and why do we pursue on that? Alright, so that is all. I hope you like the video. Thank you for watching.